All right, we are back for more, and this is going to be a lesson on trigonometry of right triangles. So in the last lesson, we learned about angle measure, and we learned about degrees and radians, and a couple of things that we could do with them in regard to circles. So now triangles are going to get involved, and we're going to continue to talk about angles in degrees and radians. Okay, let's go ahead and get started. All right, trigonometry of right triangles. So I want to start by saying that we can look at angles in circles. We did that in the previous section. We looked at angles in circles, or right triangles. And I'll show you what I mean. Remember, last time we had the definition for angle, and we looked at them starting with the unit circle, and then we also looked at just some angles in larger circles as well. All right, so here's a circle. We don't have to draw the x-axis and y-axis every time, although we could if we want to. So an angle in a circle might look like this. An angle in a right triangle. So we haven't really given a definition of right triangle in this class, but a right triangle is going to be one where one of the angles is 90 degrees. So I'm going to draw an example of a right triangle. This angle down here is what 90 degrees looks like, and we sometimes indicate 90 degrees with a little square in the corner, whereas most other angles we indicate with a little curved line, or a right angle gets a little square instead. And I could look at this angle theta. Now, when we look at an angle theta in terms of a right triangle, we might talk about the three side lengths that make up the triangle. And we name the three side lengths according to where they are in relation to theta. Theta is, there's three angles in this triangle, but theta right now is kind of the angle that we're interested in. So we're going to label the three sides. First of all, we say this is the adjacent side because it's adjacent to the angle theta, meaning it's like touching, it's part of the angle theta. And we call this the opposite side. The opposite side length is the only side that is not a part of the angle. And finally, this longest side is opposite from the right angle, and we call that the hypotenuse. So the hypotenuse is always opposite from the 90-degree angle. Remember, this lesson is trigonometry of right triangles, so we're going to assume there is a right angle. In future lessons, we might look at other triangles, so the things that we're talking about here are specifically for right triangles. The point that I'm making is not every triangle has a hypotenuse. A hypotenuse is supposed to be opposite from a right angle. So later, if we see some other triangles that don't have a right angle, then they don't have a hypotenuse. Anyway, let's talk about the unit circle. The unit circle has a radius of 1. And we know that sine of, I guess previously in this class, we typically called it something like sine of t, the t value of how far around the unit circle we go. Right now I'm calling it theta, and theta can also be thought of as kind of the t value in radians. Cosine of theta equals x, etc. So let's draw a picture of the unit circle. We'll draw the x-axis and y-axis on this one. And let's see how the circle and right triangle are related to each other. So what if I drew an angle like this, and I call this theta? It's the unit circle. So here, I'll go ahead and I'll mark this is 1, -1, 1, -1, right? Okay, let's start with this. So we start with this picture, but I'm going to add to this picture. All we have here right now is a unit circle with an angle in it. I'm going to label some things. First of all, this point here, which we typically would call the terminal point determined by t, if I take this point and draw a line segment straight down to the x-axis and stop when I get to the x-axis, do you notice that we've made a right triangle now? So every angle in a unit circle basically forms a right triangle if we do that. We just kind of added this line segment here. It's a right triangle, so I could add this little square here. What do you think the side lengths of this triangle are? The adjacent side, the opposite, the hypotenuse? Let's zoom in on this. So I claim that we know all three of these side lengths. I actually think the hypotenuse is the easiest one. The hypotenuse goes from the origin all the way to the outside of the circle. The unit circle has a radius of 1, so this must be 1, the length of that side. What about this short side length here? What do you think this side length is? Well, the terminal point we typically think of as x comma y. So it's the y coordinate of this terminal point, and look what we've got up here in the corner. Y is sine of theta. So I could label this side as sine theta. That's the length of that side. And then similarly, this side length here, just the side length of the right triangle, which stops here, it's going to be cosine, because it's the x coordinate, right? If you go from the origin to here and stop, what x value have you gone to? You've gone to the x value of the terminal point, and we said cosine of theta equals x. So that's how sine and cosine and 1 are all related to this. Now that's for the unit circle, but we also want to talk about larger circles, smaller circles, and just be more general. So let's say we have a circle of radius r. And I'm still going to assume that it's a circle centered at the origin, but it might be larger or smaller than the unit circle. All right, so we could still form an angle. It doesn't have to be this exact angle, but whatever. That angle has a name of theta. That's usually what we call an angle that we're interested in, the angle theta. So again, we could do this triangle trick, but let's try to figure out the side lengths of this right triangle. Let's start with the hypotenuse again. You know, that's the one we did earlier. I mean, up above, we said the hypotenuse was a length of 1. That 1 was because we were looking at a radius of 1. If we're now saying that the radius of the circle is r, then this side length is going to be r. How do you think that affects these two? You know, in the unit circle, they were just sine of theta and cosine of theta. It seems like sine and cosine should still play a role. I'm trying to fit both of these circles on the screen at once so that you can see how they compare. So when we went from the unit circle to the other circle, I'm imagining this being a larger circle, we kind of scaled the hypotenuse up. We scaled it from 1 up to r. So the hypotenuse was r times bigger than the old one. Well, it turns out the same thing happens with the other side lengths. This is going to be r times sine of theta, and this is going to be r times cosine of theta. It's kind of like we took the previous picture and scaled everything up. We scaled the circle up by a factor of r, so all of the side lengths became r times what they were. This also works if you have a smaller circle and, maybe r is something like 1/2, then everything gets contracted by a factor of r. Now, I want to say over here, notice that the opposite side length, we have a specific one that we call the opposite. It equals r times sine of theta. We can rearrange this equation. That is an equation, by the way. Opposite equals r times sine theta. We can rearrange by dividing both sides by r, and we get sine of theta equals the opposite side length divided by r. Or the way that it's more commonly known is sine of theta is equal to the opposite side length divided by the hypotenuse side length, because that's what r was measuring. And it turns out that all of the trig functions, all 6 of them, can be thought of in terms of either the opposite side length, the hypotenuse, or the adjacent side. And we get little formulas like this for each of the 6 trig functions. So on the next page, I'll show you all 6. And I think at this point, we're going to kind of move away from circles, and we're going to say, you know what? The triangle is really the only part that mattered here. So for the rest of this lesson, I don't think we'll draw any more circles. Let's just... You could erase this circle, and everything we said still works. Okay. Let's draw kind of a picture like we did earlier, where we just had a right triangle, an angle of interest called theta, and then we labeled this side opposite. This one is adjacent. This one is hypotenuse. And I'm going to tell you the 6 little rules that we get. Let's move this old page. 6 rules that we get. Okay, we already said one of them, so let's just write it again. Sine of theta equals opposite over hypotenuse. This is actually a useful thing because if you had a right triangle and you had an angle theta that you were interested in, if you knew these side lengths, if you knew the opposite side length and hypotenuse, maybe you know that one of them is 3 and one of them is 5, you just put them together and you just found sine of theta. So that's pretty cool. Sometimes you can do that without even knowing what theta is. Like what angle is theta? We might not even know. We might just find opposite over hypotenuse. Cosine, by a similar argument, you could start with this kind of argument like we did. And I guess with cosine, you would look at the adjacent side and you would say the adjacent equals r times cosine theta. and then you would divide both sides by r. So cosine of theta is going to equal the adjacent side. Do we say divided by r? Well, we could say divided by r, but we prefer to say divided by the hypotenuse, because then we're getting it in terms of these three side lengths. For tangent, there's a couple of ways that you could get tangent. One thing is we could still use our old rule that says tangent of something equals sine over cosine. And if you do that and cancel appropriately, you're going to find that this equals opposite over adjacent. Now, I'm going to tell you that you need to remember these. Some people like to remember these by looking at the first letter of each word. So like the S equals O over H, C equals A over H, T equals O over A. I mean, if that actually spelled out a word or something like that, then that would be nice, but it's not really a real word. But whatever method you use to help you remember these, you're going to need to know all three of these. There's 6 of them, though, right? Let's do the others. So cosecant of theta. What do you think? How can we get cosecant, secant, cotangent? I'm going to write all three. Secant, cotangent. Notice I'm writing these three in this order on purpose. Cosecant is the reciprocal of sine. So we could just take what we had for sine and flip it upside down. Hypotenuse over opposite. Right? Secant is always the reciprocal of cosine. So flip this upside down. You get hypotenuse over adjacent. Cotangent is the reciprocal of tangent. So adjacent over opposite. So all 6 of these formulas are different. But I really think you don't need to think of it as like, oh, I need to memorize 6 different formulas. I would just focus on memorizing these 3. Because if you know these 3, you could always get the other 3 just by taking the reciprocal. Remember, cosecant goes with sine and so on, and you just flip them and you're good. And if you don't remember what sine is or cosine is, you can always derive it again the way that we just did. Notice something that's cool about this. The size of the triangle doesn't matter. So what does matter? Like to find what sine of theta equals, or to find what cosine of theta equals. I'm saying it's not the overall size of the triangle that matters. The ratios of the side lengths. That's what matters. How does the opposite side length compare with the hypotenuse? What's the ratio of them? You make them as a fraction. How does the adjacent side length compare to the hypotenuse? Is one of them very big compared to the other, relative to the other? So we're talking about just ratios. I'll show you a picture here. Here's a right triangle. Now, we could draw right triangles, you know, in other configurations, but this is just kind of a common way to draw it with the right angle in the lower right. Doesn't have to be. It's just because this kind of stems from us thinking of angles in standard position. Anyway, if we were given this right triangle, and I'm giving us all 3 side lengths, and if I also had another right triangle that was much bigger, and this might not be drawn exactly to scale, but let's say we had a really big right triangle with a similar shape to that other one, but just larger. And we'll call this angle theta also. And I want to imagine that this is a side length of 40, 30, and 50. So it's like a scaled up version, right? All the side lengths have been multiplied by 10. For the small triangle, what is sine of theta? Well, relative to theta, you have to do opposite over hypotenuse. Opposite is 3. Hypotenuse is 5. 3/5. How about for this other triangle, this larger triangle? Are we going to get a larger answer? Well, let's try to do sine of theta. Here's theta. The opposite side length, which is all the way over here, is 30, and the hypotenuse is 50. So opposite over hypotenuse, 30 over 50. 30 over 50 simplifies to 3 over 5. So what I'm trying to show you is that we get the same answer. And that's what I mean with this sentence up here. It's not, the size of the triangle doesn't matter. It's the ratios of the side lengths. The ratio 3 over 5 is the same as the ratio 30 over 50. So it's possible to get the same answer for a small triangle and a big triangle. These trig functions, we've talked about these trig functions before, right? Just in terms of the unit circle. But these trig functions are sometimes called the trigonometric ratios, because we can think of them as a function or we can think of them as a ratio of side lengths. It's the same sine, cosine, tangent that we talked about in previous lessons, but we're looking at it from a different perspective. We're thinking of it trigonometric ratios. We're looking at it from a different view. All right, let's do a problem. I'm going to give us a problem, and I'll kind of get it started for us, and then I'll ask you to finish it. For the given triangle, by the way, whatever triangle I give us, it had better be a right triangle, because those are the only ones that we know how to deal with so far. Everything we've said here, you could write this in your notes if you want. These are for right triangles only. Okay? These formulas. I kind of feel like I don't even need to say that because this lesson was called Trigonometry of Right Triangles, so it's kind of implied that we're going to deal with right triangles. But yes, these formulas only work for right triangles. All right, so I had better give us a right triangle here if we're going to do a problem. For the given triangle, we are going to be asked to find sine of theta, cosine of theta, tangent of theta, cosecant of theta, secant of theta, and cotangent of theta. So we need to be given a right triangle, and we need to have one of the angles labeled theta so that we know which angle we're looking at. I am going to answer some of these. Okay, right triangle, an angle theta. We have to be given more information than just this. We have to be given some side lengths. This one's going to give us all 3 side lengths. 2, square root of 3, and square root of 7. So let me get these started. We could actually answer these in any order we want, right? There's 6 problems. You could do them in any order. I'm going to start with the first 3. So sine of theta is opposite over hypotenuse. I remember that. We sometimes abbreviate it, like opposite over hypotenuse, like that. Just because we might write these over and over again. So opposite, what's the opposite side? Square root of 3. And what's the hypotenuse? Square root of 7. So square root of 3 over square root of 7. And then we just look to see, is there anything we could do to simplify this or write it in a nicer way? I think something that would be nicer is if you have a square root on top and a square root on the bottom, we could just write this as the square root of 3/7. I think I like that better because it only has one square root instead of two square roots. Let's do cosine. Cosine of theta. Think back to those 6 formulas. This is adjacent over hypotenuse. Adjacent side length is 2. The hypotenuse is square root of 7. Let's not leave it like this, though. You know, in math classes, sometimes we don't like to leave square roots in the denominator. And a trick to fix this up is multiply it by the square root of 7 over the square root of 7. We do that to get the square root out of the denominator, because now the new denominator is going to be 7. Root 7 times root 7 is 7. And then up top, we get 2 times the square root of 7. That's actually preferred. We prefer the answer in this form. Now, you could debate, does that really look simpler than that? They each have a square root of 7 involved. Which one is really simpler? But it's just kind of the standard convention that if you're going to have a square root in a fraction, it's preferable to have it up top. Because we can think of this as 2/7 of the square root of 7. So if you find out what the square root of 7 is, you just take 2/7 of it. So it's kind of nice to have it up top. For tangent, I'm going to do opposite over adjacent. The opposite side length is the square root of 3, and the adjacent side length is 2. Is there anything we can do to fix that up? I think it's good the way it is. Let's just say that's the answer for tangent. So I'd like you to try the rest. This is a good place to pause the video, see if you can find the other 3. Okay, let's find the other 3 trigonometric ratios. So this is going to be the hypotenuse over opposite. So square root of 7 over square root of 3. And again, I'm going to combine it and make it the square root of 7/3. For secant of theta, secant is, remember, if you remember that cosine was adjacent over hypotenuse, then you remember that this is hypotenuse over adjacent. And the hypotenuse is the square root of 7, and the adjacent is 2. So that looks good. Let's just leave it like that. One more to go. Cotangent. Tangent was opposite over adjacent, so this is going to be adjacent over opposite. So we wind up with adjacent is 2, opposite is square root of 3. But again, we don't really like to leave the square root in the bottom, so if you multiply by root 3 over root 3, it's going to get it into a better form. 2 square root of 3 over 3, and that's the answer. So you see why these are called trigonometric ratios sometimes. So we answered the problem. One thing that I'm going to add, just that I think is kind of cool, is notice that we found sine, cosine, tangent, and the other ones. We found them without ever knowing what theta is. We don't even know what theta is. What is it? Is it 40 degrees, 30 degrees? What does it look like here? Looks like maybe a little less than 45. That's why I'm saying that. Is it 42 degrees? We don't know. And the point of this, one of the points of this problem is you don't even need to know. You don't need to know what theta is in order to find sine of theta, cosine of theta, and all the others. You can find them just based on the side lengths from the triangle. Pretty cool. Maybe later in another section, we might have a follow-up question that says find theta, but we're not there yet. We need to talk about solving a triangle. Solving a triangle. We've already kind of started doing this, so let's talk about it. A triangle has 6 parts. 3 angles and 3 side lengths. Seems fair, right? Each of those angles could be thought of as a number, either in degrees or radians, and each of the side lengths can be thought of as a number, usually just a number of units. Solving a triangle means finding all of these when only some are given. Okay, so some of them have to be given. You can't just have a problem where nothing is given to you. So of the 6 pieces of information, we'll be given some of them, and we'll be tasked with trying to find the rest. There are a few things that we can use to solve a triangle. I'm going to tell you 3 things we could use for now. We can use trig values we know, such as sine of 45 degrees. Do we know what sine of 45 degrees is, by the way? Maybe it's easier if I rewrite this in terms of radians. Do we know what sine of pi over 4 is? Okay, so that looks more familiar. We've done sine of pi over 4 a bunch of times. It's the square root of 2 over 2. So whether it's in degrees or radians, we know that answer is square root of 2 over 2. That's going to be useful for solving some triangles. Another thing that we can use, number 2, is actually going to be a really simple fact that we haven't said yet in this class. It's a fact from geometry that says the sum of all 3 angles must be 180 degrees. So that's an important fact about triangles from geometry. I guess, by the way, this is an important fact in Euclidean geometry. If you were to take like an upper level math class, we have a class called modern geometry. In modern geometry, we sometimes look at non-Euclidean geometry, and all kinds of weird stuff can happen in non-Euclidean geometry. But anyway, in this class, we're doing Euclidean geometry, where the sum of all 3 angles must be 180 degrees. That means that if you know 2 of the angles, you can find the third, right? If you know 2 of them, you just figure out what the third one is to make it all add up to 180. So that's good. The third piece of information that can help us is the Pythagorean theorem. The Pythagorean theorem is a theorem for the side lengths of right triangles, so it's perfect for us to use. It says if you have a right triangle and the side lengths are labeled A, B, C, then A squared plus B squared equals C squared. And this is going to help us with some problems. It basically means that if you know two of the side lengths, you can find the third one. If you know any two of the side lengths, you can find the third one using the Pythagorean theorem. Because you could rearrange the Pythagorean theorem to solve for A in terms of the other two, or to solve for B in terms of the other two, or to solve for C in terms of A and B. So if you know two angles, you can find the third angle. If you know two side lengths, you can find the third side length, and you can use trig values that we know. So let's do an example problem of solving a triangle. And I think I'll do this one. And I might have a different one for you to try a little later. So this is solve the triangle, and we're going to be given a triangle that looks like this. I'm going to do this one for us because this is the first time we're doing this, and that is what we're given. It's a picture, and we can answer it based on the picture. So I said that there are 6 pieces of information for a triangle. There's 3 angles and 3 side lengths. How many pieces of information are we given here? How many pieces of information are we given? Out of those 6, we have 3 of them, right? 30 degrees, 90 degrees, 14. So we have 3 pieces of information. We want to find the other 3 pieces. So we can find the other stuff in whatever order we want, I guess. Maybe first, let's find the missing angle. $30 degrees plus 90 degrees plus the missing angle has to add up to 180 degrees by fact 2. So that means that this must be 60 degrees. That's the only thing that could go there that's going to make this add up to 180. All right, so maybe what we'll do is, how about this? Since we need to find all of the pieces of the triangle, how about we start labeling what we find, and I'll draw a separate picture. So we have the original problem, and then we have the pieces that we find. So we just found that this angle up here is 60 degrees. And since the original problem had degrees, I'm going to leave this one in degrees also. Solve the triangle problems are usually in degrees, not radians. And we don't have to write 90 degrees next to this because that square already indicates 90 degrees. So all 3 angles are done. We need to find the other side lengths. If we had 2 side lengths, we could use the Pythagorean theorem to find the third. But we don't have 2 side lengths. We only have 1. We have 14. So we need to use strategy number 1, which we said a minute ago. Use trig values that we know, such as sine of 45 degrees equals whatever. This is 30 degrees. So let's use sine of 30 degrees. Now, I'm going to say we'll try sine of 30 degrees. If that helps us find some of the missing side lengths, that would be great. If it doesn't help us, then maybe we could try cosine of 30. Or maybe try tangent of 30. And we'll figure out, one of them is bound to help us. So sine of 30 degrees equals opposite over hypotenuse. How about this? These missing side lengths, let's give them names, because we need to refer to this and refer to this. We could call it adjacent, and we could call it opposite, but in terms of the Pythagorean theorem, maybe we would call this A and B. So I'm going to label these A and B. Maybe think of them as A, B, and C. So opposite over hypotenuse means this is B over 14. So B is equal to 14 times sine of 30 degrees. Do we know what sine of 30 degrees is? How about this? I'm trying to find B right now. So if I could find what sine of 30 degrees is, then we would find B. How about we convert it to radians? Well, scratch work. Scratch work. 30 degrees. I want to get this into radians because I'm more, maybe we say at this point in the course, we're more familiar with trig functions of radian values. So this is pi over 6. Pi over 6. Does that help? I think that does help because then I say, oh yeah, we know sine of pi over 6. That was one of our common values. That's going to be 1/2. You could even draw a little scratchwork unit circle if you want to find sine of pi over 6. All right, 14 times 1/2 is 7. So we just found that B is 7. Okay, there's only one thing missing. Only one thing missing. We need to find A. I'm going to tell you that when you're solving a triangle, sometimes you have choices, and there can be more than one way to solve it. We could find A. I think we could find A by doing this kind of work, but using cosine instead. We could try to use cosine of 30 and work through it, and eventually we'd be able to find this. But another option is the Pythagorean theorem, okay? Because we have two side lengths. We know two side lengths. So we can use Pythagorean theorem to find the third. I think that's usually easier. So in this case, a squared plus b squared must equal 14 squared. And we just found b is 7. So a squared plus 7 squared equals 14 squared. So can we find a from this? If we could find a, then we're done with the problem. A squared equals 14 times 14 is 196. 7 times 7 is 49. That's a squared. We need to find a. So a squared is 196 minus 49 is 147. And we can find a. So if a squared is 147 and we want to solve for a, usually in a math class you would do a square root of both sides. And when you do a square root of both sides, you would usually get a plus or a minus symbol. Plus or minus the root of 147. However, in this case, I know that a is the side length of a triangle, so it can't be negative. So I'm only going to write the positive case. It can't be negative something. We can't have a triangle where one side is 7, one side is 14, and the other is negative root 147. It has to be positive. The remaining thing to do here is, can we simplify this at all? Can we simplify this? You know how to simplify square roots. Well, first of all, the square root of 147 is not, it's not an integer. So we can't just evaluate it as like a whole number. You could say, you know, is 147, what is it divisible by? I can tell that it's divisible by 3 because it's almost 150. It's one less than that, right? So actually, isn't this 3 times 49? That helped because I noticed it was divisible by 3. Oh, you know what? We know the square root of 49. It's 7. So 7 square root of 3. That is considered simpler than saying the square root of 147. 7 root 3. So let's write this here. A is 7 times the square root of 3. So we did solve the triangle, and there's 2 ways that we could write the answer. I guess you could list all of the pieces, like all 6 pieces, but I think that it's okay for this problem to say this is the answer. We found all 6 pieces of information, and they're all indicated clearly right here. All 3 angles, all 3 side lengths. So, so what good is solving triangles? I want to tell you that we can use this. To answer some real-life questions. There are actually a lot of real-life situations that involve right triangles, even though it might not seem like it at first. So I'll show you a problem. A flagpole casts a shadow 42 feet long when the angle of elevation, we're going to need to talk about what that means. When the angle of elevation of the sun is 30 degrees. I'll do this problem for us. What is the height of the flagpole? All right, for this problem, we've never done one like this before, so I'm going to talk us through this. And also, I want to use this to explain to you what angle of elevation means, the angle of elevation of the sun. I'll give you a chance in case you're writing that. I like this problem because it doesn't seem like it has anything to do with triangles. It doesn't mention anything about triangles or angles or side lengths. I guess it uses the word angle, but where's the right triangle in this picture? So it doesn't necessarily give us a picture, but I think it's going to help if we try to draw one ourselves. And by drawing this picture, I'll be able to show you what the angle of elevation means. So let's assume that the ground is flat, and we're going to draw kind of a side view. Here's the ground, and we'll draw a flagpole. All right, so flagpole, flag at the top. And what's happening with the angle of elevation of the sun is that there's an angle being formed here with the top of the flagpole. And the sun is in this direction. And this angle is 30 degrees. All right, so that is what this sentence was saying when it says the angle of elevation of the sun is 30 degrees. It means the angle that's made with one of the rays being the ground and the other ray going from the ground to the top of the flagpole, to the sun. Where's the shadow in this picture? Well, if the flagpole is here and the sun is to the right of it, then the shadow is to the left of it. And in fact, the shadow is this length. The problem tells us that this is 42 feet. I'm just going to write 42 for right now. In the final answer, we'll write feet if we need to. By the way, when I said we were going to assume that the ground is flat, we should also assume that the flagpole goes straight up. So if the flagpole goes straight up, it makes a 90-degree angle with the ground. So we can mark that 90 degrees. What is this question asking? What is the height of the flagpole? So it wants to know this, we have a triangle, a right triangle, and it wants to know one of the side lengths. Let's label it. Let's call it B. I'm calling it B because I tend to think of triangles as A, B, C. But you could call it something else if you want. You could call it Y. Is there anything else we know? I guess we know this other angle here, don't we? Because if this is 30 and this is 90, this has to be 60. We'll keep that in mind just in case we need it. But I don't even know if we'll need it. I think the 30, the 42 is going to be enough. Let's think about this. We want to find a missing side length. If we had two side lengths, we could find the third one, but we don't have that. So we need to resort to that idea of using trig values that we know. Maybe we could use sine of 30 or cosine of 30. So here's what I'm going to say. Let's try sine of 30 degrees. Sine is opposite over hypotenuse. Is that going to help us? Opposite side is B. The hypotenuse. Let's label the hypotenuse, I guess. We could label it C. B over C. We don't know either of these. B, we don't know. C, we don't know. So we can't really use this because there's too many unknowns. Earlier when we used sine of, what was it? It was sine of 30 degrees, wasn't it? That was in a problem where we knew the hypotenuse. But in this problem, we don't know that. So let's move on and say sine of 30 degrees doesn't really seem helpful. So maybe we could use cosine of 30 degrees and see if that helps. Cosine of 30 degrees would be adjacent over hypotenuse. The adjacent side to 30 degrees is this 42. And we don't know C. Okay. Okay, wait. So look at this. Cosine of 30 degrees, which I think we could figure out what that is as a number. It equals 42 over C. I'm going to say that we could use this to find C. But C is not really what we're looking for. C is this length. That's not what we're looking for. We're looking for B. So then we'd still need to find B. And maybe we could do that, actually. If you find C, then you would have two of the side lengths, and then you could use the Pythagorean theorem to help you find the third. So that is one option. But I'm going to show you another option that I think is better for this problem. I'm going to try tangent of 30. Tangent of 30 degrees is opposite over adjacent. The opposite side is B. The adjacent side is 42. So I like this because we can use this to find B. We don't even need to find C along the way. We can just go straight for B. So sometimes in word problems, it helps if you try all three of these and see which one of them is going to be the most helpful. Sine, cosine, or tangent. It depends on the problem, and it depends what information is given. In this problem, tangent, I think, is the best. So from this, what have we got? From this, we could say tangent of 30 degrees is B over 42. So B is equal to 42 tangent 30 degrees. So if we can find tangent of 30 degrees, then we're basically going to get the answer. Let's go ahead and convert it into radians because I'm still thinking of trig functions mostly in terms of values like pi over 6, pi over 3, pi over 2, that kind of stuff. (42 times, what's tangent of pi over 6? We could think of it as sine of pi over 6 over cosine of pi over 6, right? You can always think of tangent that way. Maybe that helps because then you say, oh, I know what each of those are. Sine of pi over 6 is 1/2. Cosine of pi over 6 is the square root of 3 over 2. Technically, we found B, but we'd like to definitely try to fix up this answer. It looks pretty messy. We have something over 2 and then something over 2. We could cancel those 2's. Either cancel the 2's because they're both on denominators, or you could just say multiply this whole thing by 2 over 2. Either way, you're going to get this. Right? Or 42 over the square root of 3. But I don't like having a square root in the bottom, so I'm going to multiply by root 3 over root 3. And then I think we'll get to the final answer, which is 42 square root of 3 over 3. Oh, let's do a quick check. Is 42 divisible by 3? Because it would sure be nice if it is, right? If 3 goes into 42. Yes, it does. 14 square root of 3. And I'm going to write next to this feet. That's how many feet tall the flagpole is. It's a side length of a triangle, but in the context of this problem, it represents the height of the flagpole. And we found it's 14 times square root of 3 feet. Now, how tall is that? I know that the square root of 3 is 1 point something, right? It's 1.7 something. So if you think to yourself, square root of 3 is around 1.7, multiply that by 14, you get some kind of height here. I'm going to tell you I worked this out with a calculator just to kind of check, just to get like a reality check of how tall is this flagpole. And this works out to be about 24.25 feet. 24.25. But I like the answer that we put a box around, because the answer that I already boxed in is the exact answer. It's not rounded off or anything. It's exactly 14 times the square root of 3. But the 24.25 feet, that helps me look back at the picture and do a reality check and say to myself, does this answer make sense? That the flagpole could be 24 feet tall. First of all, that does seem like a reasonable length for a flagpole. I don't know much about flagpole heights, but I think 24 feet sounds reasonable. Second of all, looking at this picture, we knew we could expect B to be less than 42, right? If this is 42, B looked like it was like maybe half of that or something. So 24 does seem like it makes sense. I encourage you, when you have a word problem, to try to do what I call a reality check at the end. Look at your answer, look back at your picture, look back at the question, and just ask, does this make sense? For example, if I had gotten an answer that was 55 feet, if I got an answer that said 55 feet, I would look at this picture and say, that doesn't make sense. How could the flagpole be taller than this shadow? It wouldn't really look like this, right? So I would say that doesn't seem right. And I would double check everything. Maybe it would still be the correct answer. Maybe it would just mean that our picture wasn't really drawn to scale. In any case, if you get an answer and it seems like there's something questionable about it, then double check things. If you get an answer that says something like 2,000, I would think to myself, a flagpole is probably not going to be 2,000 feet tall. So let's go back and double check all of our work because 2,000 doesn't seem right. Also, if I got an answer that was like 2 feet tall, I don't know, would a flagpole really only be 2 feet tall? What if I got a negative answer? Don't just give a negative answer. I've seen students do this sometimes. You know, there'll be a problem like this and they say, all right, the answer is, negative 30. And I look at it and I think, well, the flagpole can't be negative 30 feet tall. So, yeah, this answer does make sense. All right, so I'm going to give you a problem to try here. Maybe there'll be 2 problems. Let's start with given the following, find. You're going to be given a picture. Sine A, cosine A. So the angle here looks like it is not called theta. Tangent A, cosecant A, secant A, and cotangent A. Wait till I draw the picture, and I have something I want to say about it. So I guess I'll say some of this as I'm drawing it. So you know how I said that I often think of triangles as having their side lengths being A, B, and C because of the Pythagorean theorem? Well, that's actually a pretty common way to label the side lengths of a triangle is with lowercase a, lowercase b, lowercase c. And a common way to label the 3 vertices, the 3 points, is with a capital A, a capital B, and a capital C. But they might not go exactly where you expect them to go. The uppercase A is going to be opposite from the lowercase a. The side length that's lowercase b is going to be opposite from uppercase b. I'm labeling these vertices, and then the uppercase C is going to be here. Now, this problem is asking us about sine of A, cosine of A. So it seems to be treating capital A as an angle, whereas a minute ago I was saying capital A, B, and C are these vertices, that those are like the points. That's okay. We do think of this as being the angle A. All right, and then, down here, this would be the angle B, and this would be the angle C, which I can already tell what the angle C is. So this is just a common way for right triangle problems to be labeled. This is the first one that we've fully labeled this way, so I just wanted to address that. From here, though, I think that you can find all 6 of these, so you should pause the video and give this a try. All right, so this one doesn't necessarily tell us that we have to solve the triangle. We might be able to, or we might not, but I think that something that's going to help us here is it would help if we knew all 3 side lengths. We know 2 of them, A and B, and I think if we're going to really find all of these trig ratios, like some of these trig ratios are going to need the hypotenuse. So let's try to find the hypotenuse first. So Pythagorean theorem says a squared plus b squared equals c squared. I'm doing a step that the problem didn't even tell me to do, but I'm doing it because I think we're going to need to know the hypotenuse. So 4 squared plus 3 squared equals c squared. 4 squared is 16, 3 squared is 9, so we get 25 equals c squared. Take the square root, but we only need the positive version of it, so c is 5. All right, good. So anytime c comes up in this problem, we're going to use 5. Let's go ahead and start answering the 6 things that it asked us for. Sine of a is opposite over hypotenuse. And it's all in relation to the angle that you're looking at. All right, this right triangle is drawn in like a different orientation than we're used to, and there's nothing labeled theta. But this is the angle of interest for all 6 of these. So from the angle A, which side length is opposite from it? The one that's opposite from it is 4. Or we could call it lowercase a. And the hypotenuse is always the thing that's opposite from the right angle. So this is a over c. And the answer to this is 4 over 5. Next up, cosine of a. Cosine of a is adjacent over hypotenuse. From A, which side length would be called adjacent? Well, I know which one is the hypotenuse, and I know which one is opposite, so the adjacent must be the other one, the 3. So we're going to say this is B over C, which is 3 over 5. So these answers look like they're going to be nice ratios of just integers, that they're not going to have any square roots involved. Tangent of A. Opposite over adjacent, which from A, the opposite one is A, and the adjacent one is B. So we need 4 over 3. For the other 3, we can do the other 3 really fast. Cosecant, secant, cotangent. I can just take the reciprocals of these 3 answers, because it's going to be c over a, c over b, b over a. So we could just take the reciprocals of these fractions and say 5 over 4, 5 over 3, and 3 over 4. I just flipped the other 3 answers upside down. And that's good. We found all 6 answers that it wanted. You see how it was helpful to find the hypotenuse first? We needed it for some of these. I guess we didn't need it for all of them, but we needed it for about half of them. No, we needed it for more than half. All right, so I think I have one more problem for you. Let's do one that's just a solve the triangle problem, because I did one of those earlier, and I want to make sure that you get to practice one. So solve the triangle, and you need to wait to see what information is given. And remember, when these pictures are drawn, they might not be exactly to scale. They'll be close enough. All right, so what I would like you to do is I would like you to solve this triangle, and you know what? I'm going to show you what format I would like the answer in, okay? You know how I said above that the common way to label the pieces of a triangle are with a lowercase ABC and an uppercase ABC? That's what I would like. I would like A equals, B equals, C equals, A equals, B equals, C equals. All right? And you can pause the video and take a minute and try this. All right, I'm gonna do a fresh sheet of paper. I think that we could find some of these pieces really quickly. Some of them are actually given to us, right? So angle A is given to us as 45 degrees. Angle B, I'm going to leave that blank for just a second, but angle C is given to us as 90 degrees. All right, so now I see what B is. Now I see what angle B is. These three have to add up to 180. So 90 plus 45 is 135. 180 minus 135. This has to be 45. That's the only way that they're going to add up to 180. I guess we also know lowercase a is 2. You know, so we could write that if we want. Lowercase a is 2. And that means that all that's left is we need to find lowercase b and lowercase c. So we have 2 pieces to find. So I don't think we could do this. I don't think we could do it with the Pythagorean theorem right now. I think we need to use a trigonometric ratio of 45 degrees, like either sine 45, cosine 45, tangent 45, maybe one of the others, but probably one of the first 3, sine, cosine, or tangent. So kind of like with the flagpole problem, you might want to try all 3 and see which one helps you, or maybe you could just mentally kind of check out all 3 and figure out which one is going to help. I think sine of 45 is the one that's going to help us, because it's opposite over adjacent. What is opposite of 45 degrees? It's 2. And what is the adjacent side length? The adjacent side length is here, which we call lowercase b. I'm sorry, I have a mistake here. Let's fix this. You might have heard a little hesitation in my voice because I was like, wait a second, this doesn't seem right. Let's take a step back. Do you see what I did wrong? That's the wrong formula for sine. It's not opposite over adjacent. Sorry about that. Let's fix it. This is opposite over hypotenuse. I think I was looking at a different area in my notes. Anyway, opposite over hypotenuse. That's better. What's the hypotenuse? The hypotenuse is going to be lowercase c. All right, sorry for that. Mistakes do happen, but when you make mistakes, try to catch them quickly. I guess that's my advice to you. Everybody makes mistakes in math. The important thing is to catch them. All right, so what have we got here? Sine of 45 degrees equals 2 over c. So we're going to use this to find c. c is 2 over sine of 45 degrees. We know what sine of 45 degrees is, right? Because we did it earlier today. You could convert to radians if you want, but I think we already did this, and we found that this was the root 2 over 2. Of course, I don't want to leave it like that. I want to try to fix this up. What's a good way for us to deal with this? Maybe we could write it as 2 times... let's multiply by the reciprocal. Instead of dividing by a fraction, multiply by the reciprocal. So 2 over the root of 2. 2 times 2 is 4. So we know part of this, right? This is 4 over the root of 2. That already looks better to me. But I think we could make it even better if we multiply by root 2 over root 2. It's going to make it even better. So I get Up top is 4 times the square root of 2. On the bottom is 2. And finally, 2 root 2. That's my answer for lowercase c. Maybe we go up here and let's maybe, since we have 4 of the 6 pieces up here, how about we just go in and fill in the answers as we find them? Maybe that's a good idea. 2 root 2. This is going to wind up being our finished solution, but we still need to find b. Okay. We have options. We have options for how are we going to find b. The options that I can think of are we could try to use another trig function. We could maybe try to use cosine or tangent and see if that helps us find b. Or we could use the Pythagorean theorem because we have 2 of the side lengths and we're trying to find the remaining one. When I'm given the choice, I usually prefer to use the Pythagorean theorem. I know it means that you need to figure out some square roots, but I think ultimately it winds up being easier. So a squared plus b squared equals c squared. In this case, that's going to be 2 squared plus b squared equals 2 times the square root of 2 squared. We'll use this to find b. No sines or cosines or tangents needed. We just need to do some algebra. 2 squared is 4. How about this? What do you think this is? 2 square root of 2 squared. Well, when you have something in parentheses like this and you square it, you have to square both pieces. So the 2 gets squared and the square root of 2 gets squared. When the 2 gets squared, it becomes 4. When the root 2 gets squared, it becomes 2. 4 times 2 is 8. So b squared is 4. Hey, look at that. B is 2. Let's go up here and write that. 2. One last thing. We found an answer. We solved the triangle because we have all 6 pieces. You should write all 6 pieces, even the ones that are given in the problem. The a equals 2 was given in the problem. You should still write it as part of the answer. The the uppercase a, that was given, but you should still write it. It's nice to have all 6 pieces written together. All right, one last thing. Let's look at the picture of the triangle and just ask ourselves if these answers make sense. This was the triangle. Does it make sense that these could be the side lengths? We found that b is 2, lowercase b is 2, so that's over here. We found this side length is 2. I think that that seems reasonable, that these 2 side lengths might be the same. If I got something here that was like 10, then I would say that must be wrong, but 2 seems reasonable. And then 2 times the square root of 2. You don't have to know exactly what the square root of 2 is, but it's around 1.4. So 2 times 1.4 is going to give me a larger side length. And it's basically saying that this side length is the longest of the 3. And that agrees with what I'm seeing in the picture. This side length is the longest of the 3. That's the kind of reality check that I like to do. If I did this and I got a really small answer for C, I would say that might be wrong because that looked like it should have been the longest side. All right, so I'll leave this here just for a moment, and then we're going to wrap up, and that's going to be it for the lesson. Okay, so that's going to be it for today. Let me tell you where we're headed with this. Everything we did today was for right triangles. And if you think about it, the angles that we were interested in, sometimes they were called theta, sometimes they were called capital A, but whatever we call them, the angles that we were looking at were always less than 90 degrees, right? Because if it's part of a right triangle, one of the angles is 90, the other two have to be less than 90. So in the next lesson, we will look at other triangles where we will look at other angles that could be larger than 90 degrees. Because, what is the sine of 135 degrees? Or, what does a triangle look like that has that kind of angle? What about angles that are bigger than 180? We could look at angles that are not even part of a triangle. So we've still got work to do. That'll be in the next lesson. So that's it for now, and I hope everybody is doing well, and I'll see you soon.